Back in the mists of time, astronomers peered up at the skies, looking for gods and wondering what it all means. Different civilizations started to observe the motion of stars, the sun, moon, and planets as the basis for clocks, calendars, and navigation. Then, about 500 years ago, the telescope transformed this ancient science. The mountains and craters on the moon came into view, as well as a ribbon of diffuse light arching across the sky, and we found our place in the Milky Way. With bigger and better telescopes, man could peer into more distant reaches of space and time. But the search to go ever further goes on, and a new type of astronomy was born. As well as the light we can see with our eyes, there are radio waves, noise, that give us a whole new insight into our universe. The first radio telescopes were enormous dishes collecting radio signals from stars, galaxies, black holes, and other astronomical objects. But even these giant structures are about to be dwarfed by a vast 21st century telescope that's about to reach Ireland.
This field on the grounds of Birr Castle in County Offaly will eventually become the most western part of a radio telescope that extends over 1,900 kilometres all the way to the most easterly node in Poland. The sheer scale of the project conjures up images of giant structures like Jodrell Bank and scenes from old science fiction movies. But when you walk through those gates, it's hard to imagine how what they're building here in Birr can ever give us a glimpse of the outer reaches of our universe.
Welcome to the LOFAR field.
When people think of a telescope, they probably think of a big tube or maybe a satellite dish, but that's not what LOFAR is about.
This is a weird-looking telescope. It's actually quite ugly, I have to admit. It looks very strange. That far end of the field is going to be covered in wires, draped off little posts, and there'll be 96 of them, all hooked by cables into a big computer. And then over here we're going to have these big black tarpaulin things and more antennas, and they're all hooked up by cables back into the supercomputer as well, and then they go in fibre the whole way back into the centre of Europe.
Why Birr?
Why Birr? Well, Birr is kind of the historical centre for astronomy for Ireland, really. But the other thing is that it's very radio quiet. It's in the Midlands. It's away from Dublin and Galway and Cork and Belfast, so the place doesn't get much radio interference. So it's a good place for doing radio astronomy. But the other thing is it's flat. You know, the sky is available to us. We can see the horizons from here. So that's a perfect place to do radio astronomy. LOFAR, in order to install it, we need a nice flat platform. And so this will provide us a place where we can set up the antennas and we know exactly where every single one is to about an accuracy of 3 centimetres.
LOFAR, short for Low Frequency Array, is a network of state-of-the-art telescopes that can observe the universe in unprecedented detail. The station in Birr will be the latest addition to this ever-expanding matrix. It's the telescope that may never be finished.
Talk to me about the size of LOFAR, because it's enormous, isn't it?
Well, I mean, even this telescope itself is quite large, you know, as things go. It's about 150 metres long by about 100 metres wide. But this is only one of 50 telescopes across Europe. And we go from here to the United Kingdom, then from the United Kingdom down to France, then from France up into Holland, into Sweden, and the whole way out to Poland. And so between us and Poland, it's nearly 1,900, it's just over 1,900 kilometres. And what that does is gives us one enormous radio telescope. And that enormous radio telescope makes it possible to see very faint things and also to see things in great detail.
So what are you hoping to see?
After the Big Bang, it left behind a huge flash. And some satellites from NASA and from the European Space Agency have seen these flashes. It's called a cosmic microwave background. What it does is it shows that the Big Bang actually had structure in it. What LOFAR will do is look at the dark ages, they're called, just after that. When the first stars started shining, it'll look at that to see if the universe actually changed from that very early period to a little bit later on. But also we'll see black holes. We'll see gas going into black holes. We'll see galaxies merging with one another. And for me, I'm going to see explosions on the sun with better detail than we've ever seen before.
Ireland's new role in the whole LOFAR adventure sees the small Georgian town of Birr reclaim its unlikely place at the cutting edge of astronomy. This place is home to what was at one time the biggest telescope in the world, and a 19th century earl who made the universe seem like a much bigger place.
There's been a castle on this site in Birr for nearly 1,000 years. It's believed the Anglo-Normans first built a tower house here in 1170. And for much of its early history, this is where the O'Carroll clan ruled over vast tracts of Offaly and North Tipperary. Then, in 1620, the Parsons were granted the castle, and they're still here. Alicia, this is such a spectacular building. Can you tell us a little bit about the castle and its history?
Yes, the Parsonses came here in 1620. We came up from Youghal. We were originally pirates, and the reason we chose Birr was it was the place where there be dragons, and we came up here, up the Shannon, by boat, and we've been here for 14 generations.
And of course, the third Earl of Ross is one of those that made his mark with that fantastic Leviathan telescope.
Yes, he's famous for astronomy, but he was also a great engineer. He built a small telescope, which was only 3 foot, and it was the biggest in the world at the time. And he then turned around and said, you know what, it's not big enough. I'm not really seeing what I want to see. And so in one fell swoop, he doubled it, which meant he had to overcome numerous new inventions. The metal technology wasn't there to make the mirror. The whole lifting mechanism and how it would move was totally unknown, so he had to invent a universal joint so it would swivel. And his wife designed the amazing walls which supported the weight of it.
And wasn't Mary Ross, the Earl's wife, very much a partner in this enterprise?
Yes, she was. She was highly educated, which was quite rare in those days for a woman. She was a very good chemist. She was a pioneer photographer, so she would have helped with the metal technology of the mirror and all sorts of other designs.
And she also funded the building of the telescope as well.
Yes, she was an heiress in her own right, so all her money was spent on her husband's and her enterprises. Not only did she build the telescope, but she built the keep gate, she put a floor onto the castle, she put the facade onto the castle, she built the moat, she built the walls. She definitely poured money into Birr.
And there's been an interest in science that's sort of run through the Parsons family since, hasn't there?
Yes, there has. The third Earl's father, the second Earl of Ross, was very much anti the Act of Union in 1800. And because of that, he decided not to send his children to be educated in England, where they would have been educated in the classics. But he educated them here in Ireland, either with other Irish families or in the workshops here in Birr. And as a result, they were all brought up very much working in workshops and being encouraged to ask questions of why and what if and find solutions. So the third Earl and Mary Countess of Ross did that to their children, experimenting, and therefore all their children ended up as scientists and engineers.
So you must be very excited about this new chapter then, bringing LOFAR to Birr. What do you think it'll mean to your family and the area?
It's so exciting to us that iLoaf is happening here. I just think all my relatives up there will just be grinning from ear to ear, thinking finally we're back at the edge of technology again. We'll be discovering what's out there, and I suspect the third Earl will be looking at all the readings over Peter's shoulder and kind of going, oh, that's what that was. No, it's incredibly exciting. We're deeply proud that it's here.
The third Earl of Ross's Leviathan telescope still stands proudly on the grounds of Birr Castle. When the nearby low-far field of antennas starts to feed unimaginable amounts of data into the supercomputer network, it will do well to match the startling contribution to astronomy made by this imposing old structure.
Let's see if these biceps work. They don't. Pretty stiff.
So this is it.
We're here.
What sort of challenges were there from an engineering point of view getting this thing together?
I think it's unbelievable what he achieved here. You've got to remember that this was the 1840s in Ireland. He had to first of all make a mirror, and this wasn't just a normal mirror, this was a 6-foot diameter mirror. And he had to work out the materials for it. It had to be reflective, it had to survive the Irish weather. The telescope itself, it's 50 foot long, and in order to get that telescope to move up and down, he had to come up with the counterbalances right, he had to get the hoists right, and with those, he was able to then winch the thing up, and that's not a small object. So as an engineer, it really is quite astounding what he was able to achieve, never mind the scientific things that he found.
It looks quite beautiful too. I mean, the stonework, is that necessary?
I don't think it is, but as you can see, the castle is off here in the distance, and I think, from the drawing room up there to have this big ugly telescope may not have been exactly what he or his wife wanted.
So how does it work?
Yeah, it's a big light bucket. What it does is, the more light you can get, the fainter the objects you can see in the sky. And what this here does, you point it up at whatever object you're interested in, and then the light comes down to the very end where there's the 6-foot mirror made out of tin and copper that he fabricated himself, and that's parabolic, so it brings the light to focus at this end here. So there's a little mirror just here, which is a flat mirror, and then the light from there goes in through the eyepiece, and then you can put your eye up there and you can see what the third Earl of Ross would have seen himself.
Yeah.
So it's really, really amazing. But the eyepieces are also enormous. They're made out of brass. There's a lot of different lenses inside those that help you bring it to focus.
Presumably this didn't move around too much. You're looking at a very specific part of the sky.
Well, the telescope can go up and down in elevation, so it can point right up at the zenith.
Wow.
So in order to get up there, you've got to climb up these ladders and then go right up onto these galleys on the top. But then they move in and out, and you can just imagine at 3 o'clock in the morning being on top of one of those, as the wind is blowing a little bit, you're rocking around, you're trying to keep your eye on the eyepiece, and you're trying to make a sketch at the same time. And also the locals don't like you very much as well at times, so you're kind of keeping the other eye looking out for people coming across the field. So it was a really challenging piece of equipment to operate and then also to make amazing observations with.
Were there any big discoveries made by the Leviathan?
Well, the Leviathan made some spectacular discoveries. The third Earl of Ross came up here in the middle of the night with a sketch pad, and he drew what he saw through the eyepiece. And one of the things that he noticed about these nebulae, which are places where we now know stars are formed, was they had structure. They weren't just blobs or fuzzy stars. There was something inside them. And the shape of the things were spirals. There were spiral arms inside this. And this meant that they weren't just gas clouds anymore. They were actually galaxies like the galaxy that we live in. And the spiral also said something else about them. It says, well, they're swirling along, they're moving, they're dynamic. So stars aren't static, the universe is all moving.
This was before the availability of photographic plates, and so the Earl did what all astronomers then did. He made careful drawings of his observations. If you look at Van Gogh's The Starry Night with the eyes of an astronomer, there is something familiar about the sky in this small painting. As telescopes got better and better with time, the Whirlpool galaxy appeared in ever greater detail. But they also revealed the startling accuracy of the sketches drawn by the third Earl high up on the Leviathan in Birr.
Why do they have spiral arms?
Well, spiral arms are created because as the gas cloud collapses, it's spinning, and it starts spinning and spinning and spinning. And as it's spinning, it kind of collects up material. And as it collects up material, it compresses it into these little bands. And the band, well, they're not very little, they're absolutely enormous bands. And it's in those bands that millions and millions, in fact, billions of stars are being born inside gas clouds. So the universe became very big all of a sudden from a man in Birr looking through his telescope. So it was an amazing discovery.
The Leviathan was the largest telescope in the world from its construction in 1845 until it was eventually superseded in 1917. Now, in 2017, Birr will be home to a new telescope that will push the boundaries once more as the latest component of a giant Europe-wide adventure. But to get to the very heart of LOFAR, you have to follow the fiber cables back to the land that's been at the forefront of radio astronomy from the very beginning, the Netherlands. This is where LOFAR was born, but just like the Leviathan, it was the brainchild of an Irishman.
Astronomers have been peering into the universe from this roof on the Academy building in Leiden since 1632. The original wooden structure was superseded by these rotating domes that scanned the skies looking for the mysteries of the universe. Nearly half a millennium later, an Irishman became professor of astronomy at Leiden and conceived of a completely new type of telescope.
Back in the 1950s, George Miley was a young boy from Dublin with a passion for science fiction and the possibilities of space travel and far-flung galaxies. He crossed paths with Stephen Hawking and embarked on a glittering career that saw him devise an ingenious way of opening up ever more distant parts of the universe.
So George, how does an Irishman end up studying astronomy in Leiden?
Well, it's a long story. First of all, how did an Irishman become an astronomer? Well, when I was a really small kid, 7 or 8, my father read me this story by H.G. Wells called The War of the Worlds. It really is an exciting thriller about a bunch of Martians that come and invade the Earth. I got really excited by it, and I wrote a letter to Professor Herman Brook, who was then director of the Dunsink Observatory, and he invited me to come out and look at Dunsink. And so this 8-year-old kid went out to Dunsink Observatory and was brought around and shown around by Herman Brook. Now that made an enormous impression on me. I did a BSc in physics, and I went on to do a PhD in radio astronomy at Jodrell Bank. At that time, it was really exciting, radio astronomy. The space program was going on. This huge dish in Jodrell Bank was very important to pick up signals from these space probes. And a particular one that I remember is when the Soviet went and made photos of the backside of the moon. And it was a really inspiring sight.
George first came to Leiden to work with the legendary Dutch astronomer Jan Oort at the newly completed Westerbork Synthesis Radio Telescope. And this is where he conceived of LOFAR.
It was in the 90s, in about 1997, I think. At that time, Westerbork, the big radio telescope, was becoming older, and one of the areas that had been really unexplored for about 50 years was the very low frequencies. Because it was very, very difficult to go deep, it was neglected.
LOFAR luidt een compleet nieuwe fase in voor de radiosterrenkunde.
With the rise of the big computers, you could build a relatively inexpensive radio telescope which would go deep at long radio wavelength.
LOFAR spans entire countries. Why does it need to be so big?
The reason is that LOFAR operates at very low frequency, and the clarity of the pictures depends on both the wavelength that you're observing and the size of the telescope. So we have an array of telescopes all over Europe, and that is the same clarity of picture as if you had a big telescope spanning the whole of Europe. The real hope of LOFAR is that it will look at the first galaxies being formed and really see how this happened. We all come from the Big Bang. Everything around us was once in this Big Bang 13.7 billion years ago. And the further we can go towards the Big Bang, the further we go towards our own roots.
The trenches have been dug and the cables have been planted as Ireland's new LOFAR telescope takes shape. Every antenna has to sprout out of the Earth in strict formation. The data gathered on this field will feed into a Europe-wide network that's nearly 2,000 kilometers in diameter. This idea of scouring the universe for static or noise is a relatively recent technology. When World War II ended, the radar scientists turned their attention from detecting the enemy to more celestial pursuits. So to try and understand how George Miley's 21st century telescope works, I need to go back in time. Back to where it all began for George in the 1960s. Back to an age when radio telescopes looked like radio telescopes.
The first radio waves from space were detected back in the 1930s, and since then, astronomers have been using radio telescopes to explore our universe. The advent of this new technology also turned a muddy field in Cheshire into one of the key sites of the space race. Jodrell Bank put Britain at the forefront of radio astronomy. This giant, iconic dish transformed our understanding of space and was a key part in unraveling that mind-bending theory of the beginnings of our universe, the Big Bang.
For centuries, astronomy used to be putting your eye to glass and looking up at the sky, but then radio telescopes came along. Why are they so important?
Well, radio telescopes offer us a view of the invisible universe, the things that our eyes can't see. To see something with our eye, and with the piece of glass telescope, we need something that emits in the optical waveband. But many physical processes are very high energy, and high energy processes tend to emit at longer wavelengths in the radio waveband. And so, to see them, you need a radio telescope.
Do they need to be this big?
They don't. They're more impressive when they are. But if you want resolution, high resolution on the sky, then you need a big telescope. And it doesn't just need to be big in physical size, it needs to be big in terms of the number of wavelengths that you can get across the telescope.
The basic technology of radio telescopes hadn't changed since the 1960s. large mechanical dish antennas collecting signals before a receiver detects and analyzes them. The larger the dish, the further you can see. But to take the next step, to unravel the secrets of the early universe, would require a dish so large that it would be completely impractical and extremely expensive. And this is why LOFAR was born. Thousands of cheap, small antennas placed in stations nearly 2,000 kilometers apart, all linked with a lightning-fast fiber network feeding a supercomputer. With some very smart software, LOFAR becomes a virtual dish, the size of Europe.
The radio telescope, in principle, is quite simple, that the radio waves arrive from space, they're reflected from the dish, and then they're collected at a receiver. And that receiver converts those wavelengths into a voltage, which we measure as a power. For a single dish telescope like the Lovell, you need to scan it backwards and forwards across the sky to create a picture. You need to literally point it in different directions to find the power there. But for the LOFAR telescope, you simply look at the same patch of sky, and because you're measuring the power on different scales, you can make the image directly.
Why does this look so much different to the LOFAR telescope?
Again, this comes down to wavelength. So the Lovell telescope works predominantly with wavelengths that are a few centimeters long, sort of this length. Whereas the LOFAR telescope works at meter wavelengths. So LOFAR can receive wavelengths that are as long as 3 London buses stood end to end. And to observe wavelengths like that, you don't need a solid dish. You can get away with a much simpler electronic receiving system.
A field of TV antennas, essentially.
A field of TV antennas or coat hangers.
It's not very impressive.
It's not very visually impressive. You can see the Lovell for miles. You probably can't see a LOFAR station until you step on it.
What sort of things do you think we can discover with a telescope like LOFAR?
LOFAR is a fantastic telescope for discovering new things. Most of the high energy processes that we observe in the radio are amplified at low frequencies, so we can see fainter things, we can see further away things, we can see less powerful things. We can see effects that happen further away from their origin, so we can see cosmic rays racing through space. And because the cosmic rays are visible at these wavelengths, we can see their interactions. And so LOFAR opens up a brilliant window on magnetism science. So magnetic fields, which we can never observe directly, are illuminated at the frequencies that LOFAR works at.
LOFAR has the power to unveil ever clearer pictures of the magnetic fields in our own and nearby galaxies. It will also track the solar wind and magnetic field conditions as they impact us here on Earth. What we see is an opening in the sun's atmosphere, a coronal hole or sunspot that allows electrons and protons to flow out. These charged particles are blown through space by solar winds. But if this deadly cosmic radiation comes hurtling towards us, the Earth has an invisible barrier. These gusts of charged solar particles are deflected away by the Earth's magnetic field. But the magnetic field is weaker at the poles, allowing some particles to enter Earth's atmosphere. These electrically charged particles from the sun collide with gases such as oxygen and nitrogen in the Earth's atmosphere, causing them to light up, creating auroras around the magnetic poles of the northern and southern hemispheres. And that's how we get the most spectacular light show on Earth. The Irish astronomers who will eventually get to peer at the skies using LOFAR will be part of a very distinguished tradition. Indeed, when radio astronomy was in its infancy, one of the greatest astronomical discoveries of the 20th century was made by an Irish astronomer at this observatory in Cambridge.
Space is a place where astronomers expect only the unexpected. At the Mallard Radio Astronomy Observatory, they've discovered little green men.
This is what a group of linked radio telescopes looked like back in the 1960s. When the Mullard Observatory that's near Cambridge came on stream in 1967, the idea was to hunt for quasars, enormous objects the size of galaxies that are incredibly bright and emit an awful amount of radio waves. A PhD student from Lurgan in County Armagh was given the task of monitoring the sky to look out for rapid fluctuations in radio waves that might indicate the presence of a quasar. But within a few weeks, Jocelyn Bell changed the course of scientific history and discovered a brand new type of star.
They're really called pulsars, stars that send out radio signals so regularly it was first thought by some that they came from intelligent beings.
Hi, Jocelyn.
Hello.
How are you?
I'm great. How's yourself?
Very good.
Good.
Beautiful room we're in.
It's lovely, isn't it? Yes.
It must have been exciting for you in this new field to be rolling up your sleeves and building a new telescope.
Building it was heavy labour. One of the skills I acquired in my PhD was swinging a sledgehammer. With a new piece of equipment, you've got to check it out very, very carefully. I was the first person to use this telescope, so I was checking every peculiar signal really, really thoroughly. And there were plenty of them. There was a lot of dross. And 99% of that dross turned out to be interference, problems with the kit, things like that. But there was one bit that didn't make sense, and I pursued it. It took some persistence to pursue it, but I did. And that's what ultimately turned out to be the pulsars.
What is a pulsar?
It's a very, very compact star. It's about 10 miles across, but it weighs much the same as the sun. 1,000 million tons. I have to count on my fingers. 1,000 million tons. It's spinning very rapidly, and it's swinging a beam of radio waves round the sky. And each time those radio waves fell on my telescope, it went blip, 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 only a lot faster than that.
Jocelyn's discovery was an insight into how massive stars eventually collapse and die. After these stars have finished burning their nuclear fuel, they undergo a supernova explosion that blows off the outer layers, leaving the center to collapse under gravity. This is a neutron star. They're only about 20 kilometers in diameter, but they have the mass of nearly 1.5 times that of our sun. A neutron star is so dense that on Earth, 1 teaspoonful would weigh 1 billion tons. And this is what Jocelyn discovered, a special kind of neutron star, a pulsar, that has jets of particles moving almost at the speed of light, streaming out above its magnetic poles. These jets produce very powerful beams of light that sweep around as the star rotates, just like the spotlight of a lighthouse. And just as a ship in the ocean sees only flashes of light as the beacon revolves, these stars appear to turn on and off as the beam sweeps over the Earth. When did the significance of what you discovered really hit you?
Oh, it came slowly. I can remember attending a conference in Boston, USA, a few years later, and finding that lots of people were working on these things and really seeing that they were an important part of the universe and could explain a number of things that had previously been inexplicable. So that's when it really hit me.
LOFAR is extending to Ireland. It's a very exciting time. Can you talk to us about why it's important to build something like LOFAR?
Well, first of all, it's going to put Ireland on the map, which is very important. The LOFAR station at Birr is going to be very important for the whole LOFAR project because of the extent out to the west. It's going to improve the definition hugely. So it's going to be very important from that point of view. But the nice thing about each of these LOFAR stations is that they're big enough and sensitive enough to operate on their own when they're not needed as part of the whole consortium. So Irish radio astronomers will have a chance for the first time to do radio astronomy in Ireland using the LOFAR station at Birr. And that's a fantastic step as well.
When Jocelyn Bell first discovered those regular blips on her telescope, it wasn't just the scientific community that got very excited. At a time when movies were full of threatening aliens from red planets, the conspiracy theories started that Jocelyn had discovered signals from extraterrestrials. She even jokingly marked the pulses on the charts as LGM1, LGM2, meaning Little Green Man 1, Little Green Man 2. But 50 years later, the search for little green men goes on. The SETI, or the Search for Extraterrestrial Intelligence Institute, was conceived in 1960. And the idea was to use the downtime on telescopes around the world to scour the skies for radio signals from deep space. Possible communications which might indicate we are not alone in the universe. I've returned to the deepest recesses of Jodrell Bank to find out how LOFAR is going to be a part of that search.
Mike, one of the great things about LOFAR technology is that it might solve one of the biggest questions we've ever known, whether or not there's alien life out there.
Absolutely. For me, that's actually the most important question, that radio telescopes like the Lovell, but also LOFAR, for example, with that fantastic wide field of view that it gives you. It sees a lot of the sky at the same time. We're now in a position, I think, better position than ever before, to start asking the question, are we alone?
How do we know what a signal from an alien planet would look like?
Well, we have absolutely no idea what a signal would look like. We have some thoughts because we know what our own artificial signals look like. When we send communications, we have a very narrow signal because a narrow signal is easy to pick up. So when you have the Voyager spacecraft or Pioneer or whatever, they send back their data. They send the data in a broadband, but next to the broadband is a very narrow signal, and it's easy for us here on Earth to pick that up. So we imagine that aliens might do something similar to that. So one of the things that we would be looking for is an artificial, very narrow signal.
Because we don't know what frequencies our extraterrestrial friends might be using to try and communicate with us, the idea is to check as many frequencies as possible. In the past, SETI has concentrated on higher frequencies, so LOFAR will plug an important gap in the search.
It sounds crazy to be talking about searching for alien life, but there's pretty good science to suggest that it's unlikely we're on our own in the universe.
I'm absolutely sure that you're right, because statistically it just doesn't seem possible. If physics, for example, the physics that we understand here, if that applies throughout the Milky Way, throughout the universe, and that wherever there are reasonable conditions for life, liquid water, for example, not too hot, not too cold, that simple life at least will arise. I sometimes wonder if we're waiting for some kind of breakthrough moment where we understand things so that actually we find that there's alien life all around us, but we're just too stupid at the moment to be able to pick it out. And we've had times in our past where that's been the case. For example, when Van Leeuwenhoek invented the microscope, he detected bacteria. We had no idea up until that point that there were such life forms, these tiny, small, simple life forms. which have dominated the history of life on this planet. So perhaps we're like Van Leeuwenhoek, we're waiting for that instrument that will sort of open up the universe and reveal artificial intelligence. And maybe LOFAR is that telescope.
And maybe the place to start will be to search for other worlds where life is possible. Planets just like ours, orbiting stars just like ours. Astronomers believe that nearly every star in the universe could have at least one planet. So that's trillions of planets waiting to be found.
Over the past 20 years or so, astronomers have been getting very excited about exoplanets, planets outside our solar system, usually orbiting another star. The scientific community was convinced that they were out there, but finding exoplanets isn't easy, typically because they're 1 billion times fainter than the stars that they orbit, and because they're extremely far away. Far too distant, in fact, for an optical telescope like this one in Dunsink. So an Irish astronomer is about to unleash the power of LOFAR in the continuing hunt for exoplanets. Eamon, you lead a team of international scientists in the hunt for these exoplanets. Tell us a little bit about your work.
My research is focused on radio wavelengths, actually. So I look at the very long wavelengths of the electromagnetic spectrum. And as part of this research, we're actually trying to do something that has never been done before, and that's to detect an extrasolar planet. So that's a planet orbiting a different star other than our sun, and trying to detect that at radio wavelengths.
We think there are billions of these exoplanets in our galaxy alone. How on earth is LOFAR going to find them?
Most planets are actually detected at optical wavelengths or near-infrared wavelengths. So that's wavelengths of light that are very short, a few nanometers maybe in length. But LOFAR is very different. We're looking at wavelengths of light that are about 2 to 10 meters in length. So a good comparison is just to look at our solar system in general. So the sun is constantly emitting material off its surface and throwing it out into the interstellar medium or out into space. And the magnetized planets in our solar system, that's Earth, for example, is magnetized, but the most magnetized is Jupiter. So this material actually flows onto these planets at very high energies and actually interacts with the planet's magnetic field. And as it does, we actually get the aurora that we're used to seeing on Earth here, for example. Another thing with the aurora is that this interaction actually produces radio wavelengths. Now, we can't see this with our eyes, but if you get a radio telescope, you can actually detect this radio emission. And actually, if you compare Jupiter and the sun at very long wavelengths, then Jupiter is actually brighter than the sun, so it can actually outshine the sun at radio wavelengths. And that's the kind of technique we're doing here. We want to look at these stars at radio wavelengths where we know that these stars shouldn't be bright. And if we get a detection, it's probably coming from the planet. Another really important thing that we can derive with LOFAR that we can't do with other wavelengths is we actually know, because we get a detection of the planet at radio wavelengths, that it has to have this magnetic field. And obviously, if it has a magnetic field, then, and if it did have life, then this life could actually flourish. It would be protected by the shield.
What are the images that we're going to get from LOFAR? What do they look like?
For exoplanets, the images themselves won't be that fascinating. They'll just be still point sources. So what we'll be looking for is actually a blip of light in some empty area of space. But LOFAR itself can actually image quite a large area of the sky at any one time. So we'll be picking up many, many background objects. So mainly objects with really high energies like black holes, but also we'll be able to distinguish the planet itself from these background objects. Old telescopes would just see these clumped together and we wouldn't be able to distinguish one object from each other. But with LOFAR now, because these telescopes are separated by such vast distances, we get this exceptional zoom, and these objects will actually move apart from each other, and we'll be able to tell one from the other.
To generate these high-resolution images, LOFAR combines signals from thousands of antennas to locate the precise location of a radiation source. It's all based on triangulation.
If this was a solitary antenna picking up radio signals from, let's say, a pulsar, All we would know is that there's a pulsar somewhere out there. But then we introduce a second antenna just 50 meters away. If this one detects the signal just a fraction of a second before that one, then we know the pulsar is in this part of the sky. And then if you introduce a third and measure the minute difference in time that it takes for it to receive the signal, and then we introduce a fourth and a fifth, and many, many more. With each antenna we add, the more precisely we can locate the pulsar.
Each international station on the network consists of similar arrays of antennas. The signals collected from each station are recorded and the data is dispatched along a fiber optic link back to the Netherlands. And as the clusters of antennas spread across the continent, more and more data was sent back to this curious building in Groningen. The Smitsborg houses the supercomputer that weaves together all the signals from every antenna on the network to create a virtual dish that's nearly 2,000 kilometers in diameter.
Every day, LOFAR scans the skies, hunting for answers to questions about the origins of our universe, the secrets of black holes, and the possibilities of extraterrestrial life. But this is a telescope that's getting bigger and better, and soon will stretch another couple of 100 miles out west to Ireland. Who knows what mysteries it is yet to reveal.
The Netherlands has a long tradition in radio astronomy, and the components that will eventually be shipped to Birr are being assembled at the site of one of the country's landmark radio telescopes, the spectacular 14-dish array at Westerbork. And inside this enormous hangar, they've got the brains of the LOFAR ready for shipping to County Offaly. And now back in Birr, the construction team has departed. And radio waves from across the universe are being gathered up by a shiny new telescope.
How are you?
Good to see you.
Yeah, well, welcome to LOFAR.
So take us through the build. What exactly has happened here?
Yeah, well, the first thing was the LOFAR container. That's the shipping container that has all the computers inside it, that receives all the signals that arrived. Behind me, we have the field of low-band antennas, and they pick up radio waves that are just below FM radio. And then the ones over here pick up radio waves just above FM radio. There's about 3,000 individual antennas underneath all that black material that you see over there, and there's nearly 100 antennas over in this field, all collecting data from the sun, which is my favorite object, of course. But there are other scientists who are going to be looking at stars, looking at pulsars, looking at galaxies, looking at magnetic fields around planets, and even looking way back onto the dark patch in the sky where you see nothing, looking right back to the Big Bang, to near when the Big Bang happened. And that, I think, is where the big discoveries are going to be.
I suppose Ireland should feel a sense of pride too, that we're now part of this much bigger programme staring back at the history of time itself.
Yeah, well, I mean, it's a €150 million international network of radio telescopes going from Ireland 2,000 kilometres right across to Poland. It's soon going to stretch up to Latvia and then maybe even down to Italy in the next number of years. And we're all part of that. We've got this 2,000 kilometre sized radio telescope. And there's bound to be a Nobel Prize coming out of that for somebody making a discovery. And the big one for us at the moment is planets, finding planets. And I always talk about when we were kids, there was 9 planets. And now there's 3,000 planets that we know about. But what about the planets that have strong magnetic fields, which are good places for life? We can see planets that have strong magnetic fields, and they might be the places that harbour life, complex life forms. And just imagine seeing some blips going in and going,
what are those things? Are they real? Are they artificially generated? Did they come from somewhere else? And I think that'd be kind of hairs on the back of your neck moment if you saw something like that.
The Birr Castle estate is now home to 2 of the world's great telescopes. The Leviathan uncovered the spiral nature of galaxies back in the 1840s. And LOFAR is ready to unveil even deeper and darker secrets. From Birr back to the beginning of time.